Enter any modern corporate boardroom, and you will hear terms like artificial intelligence, machine learning, and deep learning used completely interchangeably. This creates a dense fog of buzzwords that makes the technology seem like a monolithic, incomprehensible magic tool. Artificial intelligence follows a strictly ordered, nested hierarchy of structural methodologies. This animated diagram of 3 Russian nesting dolls illustrates the true relationship between these domains. We start with the outermost boundary of the field. That outer doll is artificial intelligence. It is the broadest possible category, encompassing any digital technique that enables a computer to mimic human reasoning or behavior. Early AI systems built in the 1990s, like accounting software automating tax calculations, did not actually think. They were expert systems, relying on rigid, branching logic trees, manually written by human programmers. If a scenario occurred that was not explicitly coded, the system simply broke. Recognizing this structural hierarchy is the foundational step for any executive. Governing modern models requires understanding exactly where their internal rules come from, rather than merely purchasing the latest software hype. This brings us to the middle doll, machine learning. Here, we change the mechanics of how the computer reaches a conclusion. Instead of a human programmer writing manual rules, we feed the computer a massive volume of historical data and a mathematical algorithm, instructing the machine to derive the rules on its own. Traditional programming is like giving a child a physics textbook on gravity. Machine learning is like letting a child drop a heavy ball repeatedly until they intuitively calculate how gravity operates without ever reading a word. Tucked entirely inside machine learning is the innermost doll, deep learning. This is a hyper-specialized subset of the field. Deep learning relies on a highly specific architecture called artificial neural networks. This structure grants it the unique capability to process raw, unstructured data that chokes standard algorithms, such as high-resolution images or dense audio waveforms. Moving the burden of rulemaking from humans to machines drives modern software scale, but this same transition introduces a level of unpredictability into enterprise environments. Algorithms do not learn in a vacuum. They require highly specific feedback loops to adjust their internal equations, and every machine learning model operates under one of 3 distinct paradigms. The first is supervised learning, which takes a teacher approach. In this paradigm, the machine is fed datasets where human operators have already explicitly labeled the correct answers. This illustrates a core pillar of supervised learning, classification, where a model sorts data into distinct categories, like marking bank transactions as legitimate or fraudulent. The other core pillar is regression, predicting specific, continuous numerical values, like the future price of a house. The second paradigm is unsupervised learning, or the explorer approach. Here, there is no human teacher and no labeled answers. The machine is handed millions of rows of raw data and instructed to find hidden patterns entirely on its own. This scatterplot visualizes unsupervised learning utilizing clustering. By independently grouping data points into hidden segments, it serves as the backbone for complex market segmentation and the recommendation engines that map the habits of millions of users. The final paradigm is reinforcement learning, which operates on a reward approach. Instead of analyzing historical spreadsheets, it functions within dynamic environments using trial, error, penalties, and rewards. Over millions of simulations, the AI receives digital points for correct actions and penalties for failures. This creates a continuous optimization loop. This loop is how autonomous vehicles navigate streets, warehouse robotics map their routes, and algorithmic trading systems execute trades. Before a single line of code is written, choosing the correct learning paradigm, whether it requires a teacher or an explorer or a reward structure, is the primary architectural decision an executive must make. If data is the raw fuel powering these paradigms, we must ask, how does a computer actually perceive it? This table breaks down a baseline dataset. The independent input variables the model evaluates, like a house's square footage or neighborhood safety score, are called features. The ultimate target output the machine attempts to predict is called the label. But machines do not see flat text or physical images. They perceive information as numbers organized into highly specific geometric scales, called tensors. This maps out geometric scaling. A single isolated number is a scalar. Stretching multiple values into a line creates a vector. Stacking lines vertically constructs a 2D matrix. Finally, layering multiple grids builds a multidimensional structure, a tensor. This geometry allows an AI to process vast amounts of unstructured data simultaneously. When analyzing a photograph, a 3D tensor lets the machine process height, width, and individual red, green, and blue color channels in a single millisecond. Translating a business problem into these multi-dimensional tensor inputs enables a direct bridge between corporate strategy and data science execution. Once a model processes these tensors to generate a prediction, it needs a way to evaluate its own accuracy. This is the role of the loss function, the machine's internal scoreboard that calculates exactly how mathematically incorrect its predictions are during training. The primary objective of any AI training cycle is to continuously adjust the mathematical equations until the error recorded by this loss function hits near zero. But every model faces an inescapable optimization crisis, the delicate mathematical compromise between bias and variance. On this scatter plot is high bias, or underfitting. The simple model fails to capture underlying data patterns. Conversely, high variance is overfitting. The complex model memorizes exact historical noise, completely crashing when presented with brand new, real-world data. Successfully managing this precise compromise between bias and variance is the operational difference between an AI model that looks impressive in a laboratory setting and an AI model that actually functions in production. Consider a chief operating officer deploying an AI system to optimize customer churn, preventing enterprise users from canceling their software subscriptions. The COO begins at the paradigm layer. They select supervised learning, specifically classification, because years of historical user data already exist, and the goal is to sort users into two distinct categories. Here, the data science team pulls flat metrics, like daily login duration and support tickets filed, mapping them mathematically as input features within a 3D tensor. The ultimate target label is derived from historical data, indicating whether that user canceled or was retained. At the optimization layer, the executive must direct the execution. If the developers build a model that flags every single user as at risk, the model suffers from high bias, or underfitting, and the team must adjust the parameters. Conversely, if the model flawlessly identifies past cancellations but fails to predict a single departing customer tomorrow, it suffers from high variance. The model has overfit to the historical noise. Effective AI leadership focuses on defining the operational paradigm, structuring the tensor, and balancing the mathematical trade-offs required to protect the business.